In our next section, we're going to talk about IBGP full mesh requirement for peering, and specifically talk about why does IBGP by default require a full mesh, and we'll talk about some of the configuration examples. So we'll go through this live on the CLI, see what this means from an actual implementation point of view, what are the potential issues that we can run into, and then we'll spend some time talking about what are the design advantages of running an IBGP full mesh, what are the design disadvantages, and then what is the combination of the two of these with combining either full mesh with confederation, full mesh with route reflection, or potentially all three at the same time in order to come up with what would be a partially meshed design. So in most cases, people assume that IBGP full mesh is bad, but in reality, that's not always the case. So we'll see in this section what are the reasons why you might want to actually use this and how this might end up in optimal forwarding of traffic as opposed to using either a route reflector or using confederation. Now, the basic problem statement to begin with of why do we even need full mesh of IBGP is based on the loop prevention. That in the case of IBGP, the basic advertisement rule says that if I learn a route from an IBGP neighbor, I cannot advertise it to another IBGP neighbor. Now, this implies that, of course, we either then need a full mesh of peerings, that we could do route reflection, or we can do confederation, which are the exceptions to these. So first, let's start with some basic configuration examples of this, and then once we see what the actual implication from implementation is, we'll come back and talk about why might you actually want to do this as an optimal design versus by default choosing to do either route reflection or confederation. So in this case, as I mentioned, with the topology as it stands, I have just basic layer 2 connectivity everywhere. We're not yet doing any IGP routing. We're not yet doing any BGP routing. So what we're going to do is basically separate the network into 3 different autonomous systems. We're going to have our main AS here in the middle that is going to be AS100. And then we're going to have 2 different external autonomous systems. Let's say that we have AS9, which is going to be on router 9, and then we're going to have AS10 that is on router 10. Now, on the back end, that doesn't show it in this diagram, I'm also going to add an additional link between these two, between router 9 and router 10, in order to use, or in order to form an eBGP peering between these. And then we'll look at the case where basically what this is simulating is that we have diverse connections to multiple service providers, and AS100 is trying to be used as a transit AS. So first, let's go ahead and just establish these basic peerings up between router 9 and 10. And then we'll look at what the implication is in the core in AS100, where most of our work is going to be done. So first, let's start on router 9. And in global config, we're just going to say router BGP 9. And we're going to be peering with 2 different routers. We're going to peer with router 7, and we're going to peer with router 10. So specifically here, the peer that goes to router 7, if we look at the show IP interface brief, pipe exclude unassigned, this is going to be on this link here. So if we ping 155.179.7, that's going to be router 7. So we'll say that this is going to be our neighbor, 79.7, and their AS is going to be 100. And then we're also going to advertise our loopback interface into BGP. So if we again look at the show IP route connected or the show IP interface brief, the loopback here is 150.1.9.9/32. So let's just say network 150.199 with a mask of /32. Okay, additionally, we're also going to have another segment that's running between router 9 and router 10. So let me go ahead and add this in. Let's say that this is interface gig 1.109. We'll say that the VLAN is 109, IP address of 155.1.109.9. And then the same thing on the other side, gig 1.109. That's going to be for router 10. And again, you can see this is one of the big advantages of using this logical topology here, using all of the .1q subinterfaces, as opposed to using physical links and then access ports on the switches, that if you want to change the topology around quickly in order to modify your example, the only thing you need to do is just add an extra logical interface in the configuration, and then you could have 3 or more routers on the same shared LAN segment, or like we have here, basically just a point-to-point Ethernet segment. So let's see, can we reach now between router 9 and 10, which we can, and we're going to add our peering here as well. So under BGP 9, we're going to say that we have the peer 155.1.109.10, who is in remote AS10. And let's do the same thing on router 10. So from router 10, we're going to have 2 different peers. Let's say show IP interface brief, pipe exclude unassigned. And these peers are going to be 155.1.108.8 and 109.9. So, of course, we always want to test just basic IP connectivity before we get into the rest of the BGP control plane, because we don't want to waste time troubleshooting our BGP peerings if there's some ACL that's blocking TCP transport, or we have the VLAN configured wrong, or the IP address wrong. So do yourself a favor, make sure you always do these basic connectivity tests, just to make sure that you're not wasting time troubleshooting something unrelated. Okay, so let's peer with router 9, who's in AS9. And then also we're going to peer with router 8, 108.8, who is going to be in remote AS10. No, 100. Okay, also we're advertising our loopback, so let's advertise network 151.10.10 with a mask of /32. And also what I'm going to say here is simply redistribute connected. I'm going to come back and talk about this a little bit later, exactly why I'm doing this. Basically, this is going to be a simplification of the BGP next hop processing problem we're going to run into. But like I said, we're going to come back to this in much more detail and talk about why might you want to advertise your connected prefixes into BGP, when do you want to advertise them into IGP, and then what is the end result going to be. So what happens with things like BGP next hop tracking and fast convergence if I hide the topology details by setting the next hop to myself. In this case, we're just avoiding the problem by just doing redistribution of all of the connected links. So someone had a question here, am I going to cover the network statement? Yes, there's going to be a separate section on NLRI origination. We'll talk about what are the different options, why would you use the network statement versus redistribution, and then some other minor corner cases, things like conditional route injection. Okay, but let's now look at the show IP BGP summary, and we should see that we have just our 2 eBGP peers established, which are router 9 and router 10. So if we look at the show IP BGP, we should see that we have our prefixes installed. We can see some of these are locally connected because it says the next hop is 0. And also there's 2 other key fields here that we need to be aware of. One of them, the most important one basically, is the greater than sign, which means that this is the best route, or the one that we're actually using. And then right next to that, where we do not see in this case a lowercase I, a lowercase I here would mean the route is coming from an iBGP neighbor versus an eBGP neighbor. So we'll talk about in the details of path selection, when would you choose one versus another, but there is going to be an implication of whether I'm learning the route internally versus externally. Okay, so let's do a basic connectivity test. Let's say, can we ping 151.10.10 when we're sourcing packets from 150.199, which we can. So basic connectivity is established for our eBGP peers, which are router 9 and router 10. So next, where we're mainly going to be focusing is inside AS100 with the full mesh of iBGP. So let's start on router 7, and we'll say that this is for BGP 100. We're going to peer with 155.179.9, and they are in AS9. And then on the other side of the network, on router 8, we're likewise in AS100. We're going to peer with 155.1.108.10 with a remote AS of 10. And if we then look at the show IP BGP, we see we have the prefixes. Right now, they're not yet considered best paths. This simply means the BGP is in the process of converging. So once you establish the peers, it does take quite a while in order for BGP to run through the path selection. We'll see that this is one of the reasons when we're talking about convergence that we want to use other alternate convergence techniques as opposed to just using the regular BGP update and withdrawal process. Now, if you look at this at the internet scale and you have your regular eBGP peer flap and you lose a full feed from them and it comes back, it can take 5 to 10 minutes or more in order for the network to reconverge. So simply because there's so many routes, it's normally inherent to BGP that it's not meant to converge quickly. Okay, so eventually we should see that the greater than sign comes in. This means that we can actually use these routes. Same thing should be true on the other side on router 8 if we look at the show IP BGP. Okay, it's not yet converged. And let's go back to router 7 and see can we actually reach any of these prefixes. So let's say ping 150.1.9.9, okay, which we can reach if we ping 151.10.10. Okay, we can reach them as well. And then let's double check on the other side. Ping 151.10.10 and 9.9. So essentially, as it stands now, we have multiple exit points outside of AS100. So there's the AS100 boundary here and here. And then we have multiple egress paths as it stands right now out to AS9. And then they're peering on the back end to AS10. So at this point, now within the internal network, we have a couple different design options. In this case, we're going to look at doing a full mesh of IBGP, but as we also know, we could do either route reflection or confederation, or we could do some sort of tunneling technique if we want to use AS100 as transport without having them to run BGP. So for example, we could say that if I want packets to be able to come in from 9 and transit out this way to get to router 10, the main issue we're going to run into is that all of the devices in the transit path will have to know the destination prefix in order to actually route the packets to it. Now, we assume in the case of IGP, this is already inherent to the protocol, because if we're all in the same OSPF area or we're all in the same EHRP AS, assuming you're not doing any filtering, you already have reachability to every single transit segment. But in BGP, it works a little bit differently, because as we saw, there is a clear disconnect between the NLRI origination in BGP and the actual routing to the prefix. So what this means in this particular case is that if we were to do a full IBGP mesh, we still need to have, first off, our underlying IGP transport in order to allow us to form the BGP peers and then ultimately to do the route recursion. So this is going to be our next step now, is that we need to enable some sort of IGP in the middle. Now, as a real quick fix for this, the only thing I'm going to do is just go to all of the routers, and we're just going to run EHRP on every single interface. So we're going to say router EHRP A, address family, IPv4 AS1, network 155.100, and network 150.100. And then I'm going to undo this config on 9 and 10, because basically I was just sending all of those commands to all of the routers. But I don't want the devices in the eBGP network to be running the IGP. No router EHRP A. Okay, so next let's look at our IGP routing path. Basically what we next care about is, can we transit packets between the egress routers that are connecting to the external peers? Or specifically in this case, can a packet get from router 7's loopback to router 8's loopback and back? Now we'll see the reason why this is very important is based on the BGP next hop attribute that's going to be reported into the network. And as it stands now, it's normally going to be one of two options. So when we're taking these prefixes in, let's assume that we now have this route coming in from router 9, and we're learning it from AS9, and this is an eBGP peering. When router 7 now takes this and advertises it into the IBGP domain, by default, it is not going to modify the next hop. So this means when I advertise the route to router 1 or I advertise it to router 5, they're going to see the next hop value as this particular link of router 9, which assumes that we actually have a route to that prefix. Because if BGP can't ask IGP to do the route recursion, we won't actually be able to forward the traffic. Now, in this case, the recursion is simple because I basically enabled IGP on every single interface. Or in other words, if we were to go to, let's say, router 6, and we show IP route for 155.179.9, we already natively have this route through EdgeRP simply because I have a network statement that overlapped with it. So as it stands now, we're not really going to have any issues with the next hop processing, and we're not going to look at the modification of it yet. We're just assuming that the underlying transport is there and IGP is able to do the recursion for BGP. So mainly we're focusing on here what is going to be the difference in the peering structure when we run either IBGP full mesh, route reflection confederation, or a combination of the two or three, and then what's the end result in traffic forwarding. Now, there's a number of different ways that we can do this, and we could simply start by, let's say we go to router 7, and we do something like this, where we go to router BGP 100, and we say neighbor 151.8.8, the remote AS is 100, and the update source is loopback 0. Then we would go to router 8 and we would do the same thing. So we would say router BGP 100, neighbor 150.177, remote AS is 100, and the update source is the loopback. So again, as we talked about the update source, the key point there is when BGP as an application binds the socket, it has to agree on what the source and destination is going to be for the TCP client and server relationship. So if router 7 is expecting the peering to come from router 8's loopback, but 8's not using that as the source of the packet, it's going to deny it. It's going to send a TCP reset. So we're assuming that we want to change this on both ends of the link, or both ends of the peering, I should say, in order for us to actually establish the peering relationship. Okay, now that we've established this, if we look at this show IP BGP, we should see that we have multiple paths out to the external network. So we have multiple paths in order to get to router 9. We have multiple paths in order to get to router 10. Now we will see specifically from an IBGP full mesh design point of view, this is the advantage of the design. IBGP full mesh gives us what's called path diversity, or essentially a view of every egress path out of the network because we are directly peering with everyone. Now we'll see that what this means from an actual traffic forwarding point of view is that a full mesh will always result in optimal egress traffic flows. And the reason why is that if all peers learn all egress paths, or all paths out of the network, it implicitly means that they know the closest egress path, and they can simply use their IGP metric in order to get to the egress router. And this again is what we call hot potato routing. The idea basically is that as soon as the packet enters the network, we want it to get it out of the network as quickly as possible. Now, when we're doing either route reflection or confederation, this design may not be necessarily true, what results in what we call cold potato routing. Or in other words, in order to get the packet out, we first route it into the core, transit it through the internal network, and then finally it ends up at some egress. But the reason why in this case that IBGP is a preferred design, or excuse me, IBGP full mesh is a preferred design, is it gives us optimal choices when we're trying to leave the network. So we'll see that when we do the rest of the peerings, basically all of the routers in this topology will know about the multiple exits. They should know about the egress path that is connected between 7 and 9. They should know about the egress path between 8 and 10, and then they can make their own independent decision on how they're going to route the traffic towards the next hop value. Now, assuming everything is equal in the IGP domain, everyone should make the same agreement on the path, and there should not be a loop in the network. However, we'll see in later cases, once we start to modify maybe running BGP over multiple IGPs, or we're exchanging IGP to our eBGP neighbors, then we can actually cause a loop in the BGP network because IBGP really doesn't have much loop prevention built into it. So simply based on this rule, it says just don't advertise the route unless you get it from the direct route source. That's what's trying to get us to get out of the network as quick as possible. So basically now we have a couple different choices. Assuming that we want to continue to do the peerings in a full mesh manner, we could just go to all of the neighbors and issue all of the neighbor statements, or we could do something like a BGP peer group or a BGP peer template. Now, the details of the peer groups and the templates I'm going to come back to later and look at what are the other applications, how do the inheritance rules of the templates work. But just for the simplicity of this example, since we're peering everywhere, I'm going to use a template to say that everyone has the same update source, they have the same remote AS, and then we're going to apply it just to those, basically to all of the loopbacks. So basically the template is going to look like this. We're going to go under BGP, and we're going to say that there's a neighbor, and we'll call this our IBGP mesh, and this is going to be a peer group. So the neighbor IBGP mesh has the attributes that include the remote AS being 100, and the update source being loopback 0. Then I could specify that the individual neighbors, for example, router 1, are in the peer group IBGP mesh, and the same is true with the rest of them. So 2.2. So let's pull this out, and I'm going to do the rest of this in my text editor. So I'm going to do kind of a sloppy config here. We'll see that the router is going to argue with me over some of the peering statements, but the ones that it doesn't need, it'll just reject, so it's really not going to make any difference. So what I'm going to say here is just we're peering with all of the routers, 7 through 8, and then, so same here, 3, 4, 5, 6, 7, 8. And then what it should do is basically argue with me saying that one of these peers is myself, and it doesn't make sense to peer with myself. But it's just going to reject that command, and it's not going to have any negative effect. So basically, I'm going to take this config and just paste it on router 1 through 8. And you can see that message here. It says, cannot configure the local system as a neighbor. But it's just going to reject that command for us. Now, if we look at the end result of this, let's say from router 8, and we now look at the show IPBGP summary, we should see that we have all of these internal peers, so router 1 through router 7, and the peers are up, but notice that we're not actually receiving any prefixes from the other neighbors. So currently, we're only receiving prefixes from router 7, who is the other edge router, and router 10, who is the eBGP neighbor. Now, this is the basis of the IBGP loop prevention, that it's saying when I have a route that comes from router 9, so router 9 in this case is our eBGP neighbor, and it gets advertised from 9 to 7. 7 passes this on to 1, it passes it on to 4, it passes it on to 6, etc. When these updates come in as IBGP, these routers are then not allowed to turn it back around and advertise it to other peers. So for example, if we were to go to router 6 and we were to look at the show IPBGP summary, we should see that we're only currently learning prefixes from the edge router, so from router 7 and router 8. If we look at the show IPBGP though, we should see that we're going to have multiple egress paths to these depending on how the ultimate path selection is going to work. And I'm going to talk about this in a second here, why they don't have multiple views. It really depends on how the edge routers are making their decisions. But the key point being, if we look at here on router 6 and say show IPBGP neighbor, and then one of the other internal routers, and look at the advertised routes, we should see that we're currently not advertising anything to the other IBGP peers. So only in the case when the route comes from an external neighbor can we advertise it to an internal neighbor, or vice versa. If the route comes from an internal neighbor, we can advertise it to an external neighbor, but by default, routes don't go between internal neighbors. Now at this point, we haven't yet actually advertised the NLRI of our loopbacks. So what I'm going to do to simplify this is just to go to the edge routers, which are router 7 and 8, and they're going to advertise the loopbacks on behalf of the rest of the network. So it's basically going to be this statement here, but it's going to be a network statement as opposed to a neighbor statement. So let's take this config, and we're going to say not neighbor, but instead we're going to say network. And then we need to specify the mask. Okay, the mask in this case is exactly /32. What this means is that when we're doing our connectivity tests, We now need to make sure that we are sourcing packets from the loopbacks because we're not currently advertising the transit space. So we'll see exactly what this means is if we were to source a packet from router 1 to ping to the external domain, we're not going to actually be able to reach it unless it is sourced from the loopback because they don't have a route back to the other networks. Okay, that should have been on router 8. So let's take a look at router 9. And on router 9, let's say show IPBGP. We should see that we have, or we start to learn a route to all the rest of the prefixes. So we have 1, 2, 3, 4. We should start to learn shortly here 5, 6, 7, and 8 as well. 5, 6, 7, 8. And let's do our connectivity test now. So let's say that we have a basic TCL shell, or a basic TCL script that says for each whatever our variable is, and that's going to be our loopbacks. So we have our loopbacks, and we're also going to include 151.99 and 151.10.10. And then we're going to say to ping $variable, and the source is going to be loopback 0. So let's go ahead and try this on everybody. Assuming that the rest of the IBGP network is actually converged, then we should have full connectivity. So we can see router 1 can reach all the destinations, router 2, and so on and so forth. We should have 100% reachability. But again, the issue would be if I were to do one of these pings and not source the packet from the loopback, when router 6 says, how do I route to get to 151.99, we go through the recursive process, we find the egress interface, the outgoing interface, and then we would source the packet based on whatever IP address is directly attached there, whatever is actually assigned. So this means that from the perspective of BGP, connectivity testing is going to work a little bit differently than IGP. You would not normally assume that someone in an external network would be able to ping the transit segment between the routers. And in most real designs, you do not advertise those transit networks. Because, for example, if I buy transit service from AT&T and I buy it from Level 3 or British Telecom, when I send packets through their network, they should not be allowing me to send packets to their infrastructure. So in other words, I shouldn't be able to telnet to the router, or I shouldn't be able to send an SNMP GET to the link segment. I'm only using them as transit to get through their network. I'm not actually trying to reach services that are directly inside of their network. And we'll see this is a key distinction between BGP routing and IGP routing. IGP routing is used to build reachability between the infrastructure links. BGP is used to build end-to-end reachability to where the actual application segments live. So for example, on router 9, it might be this LAN segment here where we have our web server, but it doesn't necessarily need to be the transit link that's going to the actual BGP peer. Now again, as we saw in the decision process, so let's look at the different routers and let's look at the show IP BGP, and let's see which are the paths that they're using currently and why. So starting on router 7, who is at the edge, router 7 has multiple routes to different destinations. It says, for example, I have a route to router 1's loopback, and I have a route to, and let's see, where is router 7? That should be show IP route 150.111. This should say, oh, I'm originating it, that's why, okay. So let's say show IP BGP again. And basically it says I have multiple ways to get to the internal networks. And let's say we're not looking at the internal ones. We mainly need to look at the external ones. So let's do this. Let's say show IP BGP, regular expression, caret, open brackets, 0 through 9, close brackets, plus, actually it should just be that, yes. Okay, I'm going to talk about this in much more detail later, how the logic of the regular expressions work and why you might use them in BGP either for filtering or for parsing the table. Basically, what this output here is showing me is to show me my non-local routes. because a local route would have a null AS path, or basically no numbers in the list here. So what I'm saying with this regex is to show me a path that starts with at least one AS, which means that it's not me. Okay, so specifically here I'm caring about what are the basically the external prefixes. And we want to look at this at the comparison between router 7 and router 8. Now, when we look at these routers, we'll notice that they actually have different views of the BGP topology. And this is actually the normal case of BGP, which is a little bit different than IGP. Like, for example, in OSPF, we assume that all of the routers within the area have an equal view of the link state database. So when they run SPF, they always agree on the shortest path tree. Now, in the case of BGP, that's not necessarily true. It depends on where you are physically in the topology and who you are directly peering with to determine what your view is going to be. So let's say, for example, that we look at specifically the route to router 9's loopback. So router 9 is originating this as a native BGP route. We can see this because it has the origin code of IGP. This means that we did the network statement for it. And it's being advertised two different ways into the topology. It's being advertised as an eBGP route that way, and it's being advertised as an eBGP route to 10. Now, assuming that router 10 chooses this as the best path, 10 will then pass it on to 8. Now, likewise, assuming 7 chooses 9 as the best path, 7 will advertise the route to 8, and then 8 will have to make a decision. It's going to say, do I want to take the route from router 7 as best, or do I want to take the route from 10? Which one is actually chosen will determine which one I will advertise to my other BGP peers. And this is the reason that in this particular case, when we go to the internal neighbors, like router 4, and we show IPBGP, its view of the topology may not be exactly the same as all other routers. And let's look at that again just for the external route. So let's say regex, caret, bracket 0 to 9, close bracket plus. And we want to look at this basically on all of the neighbors. So we can see that most of the routers are here saying to get to router 9, I'm going to use the link between router 7 and 9. But why did none of them choose to use the link between 8 and 10? So let's look at this from router 8's point of view. It says, in order to get to the destination, I have two different possible routes. I have one that is coming directly from AS9, and I have one that's coming from AS10, and AS9 is advertising it to 10. So in this case, simply based on the autonomous system path length, we're going to choose whoever is the closer egress point. Now, what this also means is that based on the best path selection rules, I will not be able to advertise the alternate path. So think about it this way. Let's now do a trace route in order to get to the loopback of router 9, and let's look at this from everyone internal to the network. To say, if we trace to 151.99 and we source it from our loopback, because again, right now we're not advertising the transit prefixes, when we compare this on everyone in the internal network, we should see that they all are following the same egress path. They're all going to router 7. Basically, what this shows us, again, is that with the full IBGP mesh, you will always by default choose the closest egress in order to reach the destination. Because when we look at the path selection, we know all overall paths. And in other cases, this is not necessarily true. It might depend on who you're peering with. It might depend on where you are in the physical topology, that you might make a suboptimal decision simply because you don't have a peering relationship directly with all other routers. Now, if we were to make a simple change, let's say, for example, that we were to go to the edge routers here, which are router 7 and router 8. And let's make a very simple change that we say when we are learning prefixes in from the eBGP neighbors, we're going to weight them, so we prefer the external routes over the internal routes. So on router 7, let's go to router BGP, and we'll say that when we peer with router 9, we're simply going to set the weight to a non-zero value. It doesn't really matter what it is. Let's say just 1. And the same is going to be true on 8 as we're receiving updates in from 10. So we'll say the neighbor is 155, 1, 108, 10, and the weight is 1. When we now show IPBGP, we should see that this external path is going to be more preferred than the internal path because the weighting is going to be higher. Now, it's going to take a minute for the attribute to actually process, and we have two options at this point. We could either just wait, and eventually when BGP does a refresh on its own, it will update the attribute, or we could ask the remote neighbor for a route refresh. So again, this is where the difference between saying clear IPBGP star in versus just saying clear IPBGP star. This is asking the remote neighbor, can you send me the updates again so I can apply my new policy onto them? If we now look at the show IPBGP again, we should see now the weighting for these routes is 1, which means that they're going to be chosen as the best path. Now, what the end result of this is going to be is that if the edge routers always choose their connected eBGP neighbor over the IBGP neighbor, then the internal routers will choose their closest internal path in order to get out. And again, what this specifically means is hot potato routing. That we're now looking at essentially the cost of the IGP metric to the next hop versus the other BGP attributes. So instead of saying find the most optimal path in order for router 4 to get to whatever the destination is, we're saying force router 4 to choose just its closest exit point. So do we want to route directly to router 8 or do we want to route to router 7? Well, it really depends. It depends which one are we closer to in the topology. Now in this case, we should see that 3 would route to 7, but 5 would route to 8, simply based on the IGB metrics. But ultimately, we shouldn't be causing a loop in the topology in any case here, because IGP would already have agreed on how are all the routers supposed to route towards the egress routers. So whether this is the next hop value being the loopback, or whether this is the next hop value being the transit link, both router 1 and 6 should already agree how are we routing towards that. Because EHRP is running the feasibility condition. We've already guaranteed that the route is loop-free. So this essentially now means that BGP is not making the decision. We're using IGP in order to say, from router 6's point of view, when we show IPBGP, look at basically what is the closer next hop. Are we closer to 3 or are we closer to 5? For let's say like 151.10.10. So if we show IPBGP 151.10.10, it says now we're going to choose the one that is best as router 10. Actually, in this case, it still does depend on the AS path. We would basically need to be looking at this from the perspective of someone who is equally reachable out both providers. So either this could be the same link to, or multiple links to the same provider, or we could be looking at someone who is equal AS hops away somewhere else in the network, and then we would ultimately be making the decision based on the IGB metric. But the main point being here is that now if the edge routers all preferred their external paths, all of the internal routers know all exit points, which we'll see when we deal with either route reflection or we deal with confederation. This is normally not the case. So the design advantage then here is that an IBGP full mesh means we know about all egress paths. We can then choose based on our IGB metric or based on the other BGP attributes, what is our closest path to the egress router, and then choose the closest exit. Now, of course, there are disadvantages of doing this. The disadvantages are more commonly thought of than the advantages, but it's important to note that there's both. In any network design, it's always going to be a give and a take. So it's not really valid to say this is a better design than another one. In most cases, it's just that there's multiple different ways to solve the same problem. One might solve one portion of the problem, one might solve a different portion of the problem, but ultimately there's never going to be a 100% correct answer, for example. Now, the main design disadvantage then of this is going to be the control plane scaling. Because if we're doing a peering to every device in the network, as the devices start to grow, the number of peerings grows exponentially. It's that n times n minus 1 over 2 full mesh problem. So if we have 10 routers, 45 peers, not too bad. 500 routers, 125,000 peerings, yeah, that's an issue. Now, not only is this an issue for the control plane to handle, the other big thing is that this is operationally hard to scale. So this means that if I want to make a change in the BGP network, I'm going to have to go to 500,000 peerings and make the change on all of them. Now, you could theoretically do automation to do this, but the problem is there's not really too many solutions that you can just buy out of the box in order to do it. So if you want to hire some Python programmers to spend a month writing a system to manage it, yes, it's going to work. But in most cases, just from an administration point of view, it's much easier to do either confederation or route reflection. In most cases, it's going to be route reflection by default. But the key point is that there are actually advantages of using full mesh, and you might choose to do that in certain portions of the network as opposed to the entire network. And this is the last example I wanted to talk about here real quick, which is basically a partial mesh BGP design. So you don't always necessarily have to choose one design over another. You can configure a portion of the network as full meshed, a portion using route reflection, a portion using confederation. Normally you don't combine all three, but there's nothing to say that you cannot. Now, the reason why you might want to do that is that for certain portions of the network, you might want that path diversity. So you might want to know about all of the egress paths and then use the IGP metric in order to follow the closest exit. Then as the network starts to grow, we can create multiple clusters of route reflectors or multiple sub-ASs in confederation, and then do some sort of inter-cluster peering or inter-sub-AS peering there without having to do a full mesh overall. Now, one of the examples of this is documented in the BGP route reflection RFC. That if you take a look at this link here, it's RFC 4456, specifically in section 11 about the deployment considerations. The big thing they say here is that the key component to understand about route reflection is that it addresses this scaling issue, but at the expense of best path selection. So it's summarizing the routing information, and the route reflector only reflects its best path. Now, the end result of this is that depending on what the multi-exit discriminator is or what the IGP next metric to the next hop is, you might choose the wrong path selection. So in their particular verbiage, in certain route reflection topologies, the route reflector approach may not yield the same route selection as that of a full IBGP mesh approach. Or in other words, if I hide the details from you, you can't make an informed decision. But again, it's always a give and a take. If I want to fully mesh the network, then it's going to be more difficult to manage. It's going to be an issue on the control plane. If I do route reflection, I'm going to hide the topology details. I might not be able to choose the closest exit point. But they're basically saying here there's nothing wrong with doing both. That within a cluster, you could do a full mesh. Then between clusters, you could use route reflection. So then if you tune your IGP metrics or your med value to prefer your intra-cluster peerings over your inter-cluster peerings, it should mean that everybody makes the optimal decision. But this is starting to get into a much higher scale view of it, of how would this affect a large service provider. Usually for the enterprise, it's not really that much of an issue. In most enterprise cases, you would just default to the edge. The edge runs BGP, and then the edge controls the egress flows or the ingress flows without having to take a full view everywhere. Basically, this example that I'm showing here is we're trying to use AS100 as transit. So packets are coming in, they're transiting the internal network, and then they're leaving. This means that everyone along the path would have to have the specific reachability information, or we would have to do some sort of tunneling like MPLS. Now, if AS100 was not transit here, we could simply say, just do BGP peering between 7 and 8, and then into EHRP, we'll just advertise a default route. Then however they choose their default path, which should be to the closest egress router, then they should just follow the closest exit path to the internet, to the BGP destinations. Okay, any questions up to this point on using IBGP as a full mesh? So again, to quickly recap the config, if we show run begin section BGP, in this case here I'm using a peer group, which again we'll also look at peer templates a little bit later that are a little bit different than peer groups, but the idea here is that if I change the attribute of the peer group, it gets inherited by all of the members of the group. So if I want to change local preference, if I want to change AS path prepending, I can do it once and now affect all of them. Otherwise, if we are doing a full mesh, then it becomes an issue operationally. If I want to make a change, I have to make it 8 times as opposed to just making it once. Okay, there's a question, is it possible to advertise all paths in iOS, including not the best routes, like JuneOS does with advertise inactive? There is an optimization for that we're going to look at a little bit later. It's called BGP Best External. And this comes along typically with the prefix independent convergence, or BGP PIC, that allows the edge router to advertise not only what its best path is, but its alternate egress or paths to external neighbors, which should inherently be loop-free. Because as we talked about previously, when you're looking at the decision between iBGP and eBGP, you should always choose eBGP, because if you're learning it from an eBGP neighbor, it means it's not in your network. It's in somebody else's network. So if you advertise the alternate external path, then you still shouldn't cause a loop, but you'll be able to do basically backup routing. So I could say choose whoever my best exit is to begin with, but then also advertise who are the other possible external exits, and then we can use these as our backup routes. Because we'll see the big issue with BGP is that if you go to converge based on the normal update and withdrawal process, it's very, very slow to do this. Especially at internet scale, where we would have to withdraw 500,000 routes, send 500,000 updates, run path selection 500,000 times before we can actually install the routes in the RIB and then download them for actual forwarding. So yes, we'll see that there are some cases where there are exceptions to the normal rules. This is one of those examples. There's also a feature that we're going to touch on a little bit later that is called BGP Optimal Route Reflection, which basically allows, and I'm going to get into this a little bit later, this again has to do with that cold potato, hot potato routing, that this allows the router basically to make a decision not based on your view of the network, but based on what you would assume someone else's view of the network. So it's kind of an odd theory, but it ends up to be that you want to do route reflection, but you don't want to end up in a case that you choose the suboptimal path. That's basically what this is trying to prevent by doing BGP ORR. Okay, there's a question, why are some of the routes showing as RIB failure? RIB failure just means that you are not installing the route in the actual routing table for some reason. So for example, like on router 1, if we show IPBGP, these routes that currently have RIB failure, this is because I'm already learning them from IGP, and then I'm also learning them from IBGP. So the IGP in this case is EdgeRP. EdgeRP has a distance of 90. IBGP has a distance of 200. It means that this one loses and it doesn't go into the routing table. Okay, that's what the lowercase r means for RIB failure. But assuming that I did the best path selection correctly and I actually chose the route, I can still advertise it. And we'll see a little bit later the reason why is that, again, there's that disconnect between the information BGP gives you and then how you actually route the traffic. Because I can give you the route and then say you need to go to someone else in order to actually get there. So RIB failure doesn't always necessarily mean that there's a loop, but it's like informationally telling you there that this is an inactive route. You could possibly cause a loop. So you need to look at the details of the topology before you continue to advertise it on. And as somebody else here had mentioned, you can also say this, show IPBGP, RIB failure. And then the reason why is we can see here, it says because of the higher administrative distance.